Okay, hello everyone, welcome back to the channel. So in the last video what we did was we developed this 2D open die forging process, and if you don't know about this you can go to the previous video in this playlist and you can watch that how we developed this. In this video, however, what I would like to do is I would like to develop a slightly complicated simulation model, as well as look at some of the perspectives or some of the possibilities to post-process the data. So first of all, what I would like to do is I would like to see the displacement and reaction forces on the die, right? So for this simulation, what I want to do is I want to see the displacement of a certain node, let's say, and what I will do is I will double click on XY data. I will create ODB field output, continue, and then I want to look at the results of a certain node. So I will click on unique nodal, and here I will go on the displacement magnitude, and then I want to select the node. So I will select, I don't know, this node, let's say, done. And then I want to plot it. So as we applied the linear deformation history, so you will see that in the beginning it was this, and then in the final step the displacement is 25 millimeters, like we expected, right? But if I want to look at the reaction force, so I want to know how much force was required to carry out this simulation. So what I will do is I will just click on the reaction force magnitude, and then I will select this reference point of the die that carried out the load, and I will plot it. So I will see that the force required to do this was this 800 kilonewtons, so something like 800 or almost 850 kilonewtons. So this was the total force required, and this is the trajectory of the force that you can see. So this is how we are looking at the results of how this is happening. Now I want to build on this slightly complicated system, and we know that there is spring back in our system, as well as we want to develop it in a way by changing the boundary conditions that we want to see the spring back, as well as we want to change the position of this die to move it on a little bit on the right side, and then press down again on the forged part. So what will happen is the first step will remain the same. We will reach at this point, then I will move this die up, move it a little bit on the right side, and then move it down again, and then I will pick it up again, and then we will see what is the final shape of the part, as well as the force that was applied, and what is the final shape of the block, and things like this. So this will be kind of a multi-step forging process with some post-processing and looking at how the stresses or strains are distributed, and how we can post-process the data from the simulations. And then of course you can go crazy, you can apply all kinds of boundary conditions, you can change your material model, you can change the shape of the die, and you can try it for yourself how the simulation model is working. So let's do that. For that, my working directory has already been set, so I will not change that. But what I will do is, in this model, in the same model, I will just copy this model, and I will rename it Forge 2D multi-step. Okay, so now I have created a copy of the previous model, so I do not have to make all these parts again, and I will just modify the things I want to modify, and then I can run the simulation again. Again, if you haven't seen the previous video, you can go and watch that. In that I have in detail explained how we are creating this model, and step by step. But in this one we will just modify this model to define the boundary conditions as I discussed before. So yeah, so the first thing that we want to do is we want to define multiple steps, and for that what I will do is I will define the steps here. So again, you will see that initially we had the initial step, and then the forge step. And in the forge step, what I am trying to change is that after it has deformed the part, I want to move the die back up again. So what I will do here is that initially I will change the time of this step. So I will change the time to be 2 instead of 1. And then what I will do is I will change the amplitude. So there are multiple ways of doing it, but I will use the amplitude. And the amplitude is on 2, it is minus 0.5, which means that initially it will be 0, 0, then at time 1 the die the displacement will be full 25 millimeters like we have defined in the boundary conditions, and then at time 2 it will be in the negative direction, minus 0.5, then that means the half of 0.2 will be applied here. And that is how we will move the die downwards first and then upwards later. So this is the first step. And then the second step which we want to define is move it on the side and then bring it down again and then take it up. So moving on the side is a bit tricky. We will see how we can manage that, but let's try. Let's create another step in which we just move it on one side, which will be very simple step. So move die move. I will name this step as this. Okay, so in this the time period is 1, incrementation is unlimited, mass scaling I don't want to apply any mass scaling, I just want to press OK. And now in this I again have to create, so this was linear, now I have to rename it, so it is not linear anymore, now it is down up amplitude, and I will create new linear amplitude, and in linear amplitude time 0, amplitude 0, time 1, amplitude 1, so it is a ramp. And in the boundary conditions I will right click on manage, and here I will create a new boundary condition which will take place in this step. So I will create die move, displacement rotation, continue, and so for this one what we want to do is we want to use a linear one, and for u1 we just want to move it in x direction. Let's say we want to move in positive x direction 10 millimeters. Okay, so only in this step it moves 10 millimeters. Now lower die is propagated, this one is deactivated, so this upper die first part will not take place in this step, possibly. Okay, and then we want to create again, so this is getting a bit complicated, but we will see. And then we want to move this part downwards again, and then I will say move upper, again, and then I will apply displacement, continue, and I want to apply displacement on this reference point, and in u2, and then I do not want to apply, yeah, okay, let's apply 25 millimeters downward, and then I will apply, okay, minus 25 e minus 3, and down up amplitude. Now the problem is that to do this, this is not possible. I have to create another step. So what I will do is, in this one I will just fix it, and I will propagate it in the later one, and then I will create another step which will be forge2, and here I am again defining time step as 2, incrementation with the maximum value of 0.02, and with mass scaling of 1e5, because here we will do displacement, and then inactive, and here when it is, I want to deactivate it here, and in this one I want to change it to -25 e -3 and down up. Okay, so this tree is a little bit complicated, but what is happening is that the lower die is fixed throughout the model, and the upper die initially, as we discussed in the last simulation, so it moves down 25 millimeters, and now it moves up 12 millimeters, half of 25 millimeters, and then in the next step the die moves 10 millimeters to the right, and in the step after that it again moves down 25 millimeters and then 10 millimeters back up, or 12 millimeters, half of 25 back up. So theoretically this is how we have defined the boundary conditions, this is how it should work, and yeah, now let's see what happens. So I am not changing any mesh, the mesh is same, I am not changing any boundary conditions other than this, I am not changing the material conditions, so I've just defined this new model with slightly changed boundary conditions, and I want to forge 2D multi-step. Okay, so let's see if we can run that. It is also new for me, so we don't know, maybe we will be able to successfully run it, maybe we will get an error, but then we will try to resolve it. Okay, so it is running. Okay, yeah, so we get this error. That one node df on which velocity, displacement, acceleration based constraints are specified simultaneously, the nodes have been identified in the, so it says that so okay, so what happens is that in this die move we have created, we want this die to move to one place, and also we have defined here that we want to keep it fixed, so that is why these are two conflicting boundary conditions, and therefore it will not run. So what I want to do is I want to delete this, and I want to then create it again in this step. So move upper again, and displacement rotation forge 2, continue, and I want to apply it on this one, and it is just u2, u1, and this one is 0, and this is -25 e -3 and down up, and okay, and yeah, dismiss. So now this should be, that error at least should be resolved, because now there are no conflicting boundary conditions. And now let's see. Okay, so we have another error which says original degree of freedoms. So I basically have to define a boundary condition just using one. Okay, so that means that I cannot define multiple boundary conditions, because yeah, it happens. I cannot define multiple boundary conditions because for this boundary condition to execute, it does not have a base boundary condition. So what I will do is I will do the following. I will remove this, okay, and I will remove this. And now what I will do is for the upper die here, I will activate it, but I will modify it. So it says that first I have to change this. So in this one, I am defining it as down up, okay, and then here I do not want it to move in this direction. I will make it 0, but in this direction I want to move it to 10 millimeters towards X direction, okay, with linear amplitude. And then again I want to use the down up, and here this is 0, but this is minus 25e minus 3 with down up, and now then it is modified here. So I have different steps, but in each step the lower die is fixed, but for the upper die I have defined that first the boundary condition is moves down 25 millimeters and then it goes up, then it should move 10 millimeters on the right, and then it should again go down 25 millimeters and 10 millimeters or 12 millimeters up. So now I have defined everything in just this one step by modifying it for every case, and now I will dismiss it and I want to submit and see. So the error which we were getting should now be resolved. Maybe we will get another error. So it is also very interesting to note that how error debugging is happening, because you have to understand what we have defined, what we changed in the model, and now what is happening. Okay, so this is step 1 and now this is step 2. So the simulations have gone okay, and now the step 3 is going on and the simulation has completed. Okay, so now there were no errors, only a few warnings, and yeah, so the simulation completed. Now let's see if we got the results that we expected. Okay, and where is our die? Oh, okay, so let's see what is happening. So initially it is going down, then going up, and then it is moving a little bit on this side, and then it is pressing it again. This is funny. This is very funny. Okay. Yeah, so theoretically we were able to do that, but in any case our die is going too high and then coming back again. So we want to change a few things in the model. So the first thing that we want to change in the model is we want to define a new interaction property with the lower die and the upper die. The new interaction property with the lower die again is friction lower die contact, and here in this one we want to define a friction coefficient of 0.5 like we did before, but we do not want to allow separation after contact. So once it gets in touch, it stays in touch with that surface. Okay, and what we want to do is we want to change this contact property interaction between these surfaces to this friction lower die. So now this is slightly changed. The second thing that I want to do is I want to make sure that my die is not moving too high up again. And what do I need to do for that? I will need to look at the boundary conditions and the amplitude. So down up is minus 0.5. Minus, if I move it to minus 0.2, means it should go up less. Let's try this. And then I want to submit this job again and see if we can get better results this time. So what we did was we defined this contact to be non-separable, one, and then we theoretically what I tried to do was I tried to reduce this moving up from 12 to, let's say, 3 or 4 millimeters, 4 millimeters. And now our step 2 is completed, and now our step 3 is going on, and that is also completed. So let's look at the results. And I don't know, so it goes down, it goes up again, but there was still separation. And okay, there was still separation. And what I can also do to control this behavior is I can apply a boundary condition to our part. So I can create a new boundary condition for our part in the initial step, symmetry, axisymmetric encaster in the initial part, and I can call it pinned block. So then I can choose this point and then fix it. So now this part will not move, and we will only have this die coming down again and going back up and then coming down again. So we will see how this performs, but of course it will have an effect on the results of this node now, because now this node is restricted. It is not able to move in any direction. So when we will start to forge it, it will have stress concentration. We will see. Okay, so again it completed. Let's look at the results, and now we will see that there is a small dent here, but yeah, not too much. So what is happening here now is it goes down, it still goes up. Okay, and it comes down again, and it is still going too much up. Okay, so we want to see how much it is coming down and how much it is going back up again. So what I will try to do is I will again try to plot the XY data of displacement, and I want to select this, and it is going I don't want to select I just want to see the absolute value instead of magnitude. I want to see U2. So I select this. And plot. Okay. So what is happening here, it is coming down 25 millimeters, but then it is going back to 0 and a little more, which is wrong. And then from there it is coming down 25 millimeters again, and then going back up 25 millimeters, then a little bit more. Huh. I don't understand this. Okay, so this means that there is something wrong with this amplitude that I have defined down up. It is coming from 0 to 0, at 1, and at 2 minus 0.2. So this should be minus 1.5. Let's submit this. This is tricky. Normally what for real simulations, what I would do is I would write mathematical equations and make graphs, and then calculate these amplitudes and magnitudes of these amplitudes, the boundary conditions. Here I'm just doing it out of my head, just a ballpark figure, just to show you how this is done and doable. And therefore we are having problems, but in any case we will see. Maybe this time it is better. No, this isn't. So it comes down, it goes up, so up, and then it comes down again, and it didn't even touch the second time. Okay, so this so this was right. So this was right. I will just give it a try one last time, and then yeah, you can play with it. So you see that changing this amplitude it changes this behavior. So in 2, our given boundary condition is minus 25 millimeters. So I don't want to write minus, I just want to write 0.5, which means it will go back to its initial state. Okay, so I don't have to write minus. Once I just write 0.5, it means half of the applied boundary condition, so it would automatically go back. Okay, let's see if it is better this time. So step 1 is completed, now step 2 is completed, and now let's see what happens if the total energy changes in step 3. Yeah, okay, so deformation probably took place, and now let's see what are the results, and we see that what we expected. Okay, so this is interesting. It came down, it went up, it went soundways, and then it came down again. Yes, that's exactly that we were planning to simulate. Okay, so you see here what is happening, how the deformation is taking place. And now for this I will just go to the last frame of this step. So one thing that you can do in the post-processing is results step frame. Here you will have all the different steps, and there you can navigate to all the different frames. But if you go on the XY data field output, there you can run results for all frames or steps. So if I see U2 for this point, I can plot it. So I can see that it came down, it went up a little. Here it moved sideways, and then it went down 25 millimeters, and then it moved up again. Okay, that's interesting. And the second thing that I want to check for this same same node is the reaction force. I want to see the magnitude, but you can also see the absolute values. And here we see that initially force of this magnitude was applied, and then no force is being applied, and then when the step 3 starts, there is a very high amount of force that is applied, and then again no force is applied. So there is a little bit of the spring back. That is why these values are a little bit slightly different. And that is the next thing that we want to see here. So we will see the displacement of this top node to see how the spring back or the displacement was taking place. And for that, what I will just quickly do is I will select U2 again, edit selection, and I will plot over this. And you will see that initially it was deformed, and then it just moved a little bit, and then it was deformed again, and then it moved a little bit back up. So it is hard to see in this figure because the displacement is too high, but you can get the idea. And this is the stress strain response that we actually gave to the simulation as a material data that we can see here. Then we can also see the stresses, strains, equivalent plastic strain, to see how the strain is overall distributed in the model. And you will see that here almost there is very less strain, but at this point there is very high strain, and then it is also divided in the rest of the part. This is the true strain, and we can see how that is distributed along the material surface. And yeah, so you get the idea. We can also get the velocity gradients of the parts and the block. It will be easy to see how the material is deforming and what were the velocity gradients then. So this is basically the strain rate we are looking at, how the strain rate at how the displacement rate at different points was changing throughout the forging process. And this defines how the material recrystallizes and its properties are affected after it is forged. So you get the idea now. And yeah, so you can run this simulation, and in this simulation you can apply different, again you can also try different boundary conditions, different material parameters, and yeah, then you can see for yourself how the simulation is working and how applying different boundary conditions is helping you. So yeah, if you have any questions from this simulation, or you want to know more about any other methods or techniques, you can always write in comments. You can reach me on the below given details in the description of this video. And yeah, happy simulating, and then see you later. Bye.